Hello everyone, my name is Ludovic Pascal and today I'm going to talk about the influence of hypoxia in the St. Lawrence Estuary on the bioturbation activity of macrobenthic communities and on the sediment biogeochemistry. But first, a short definition of what is bioturbation and why it is important in the functioning of benthic ecosystem. Bioturbation is basically the study of behavior of benthic organisms, and more particularly the consequences of this behavior on the sediment matrix. Indeed, through their locomotion and feeding activities, benthic organisms transport sediment particles, that is particle mixing, but also solutes in the sediment pore water, that is bioirrigation. And by doing so, these organisms transport freshly settled organic matter deep in the sediment column and introduce oxygen in otherwise anoxic sediment. And now, let's talk about the topic of this presentation. The deep water of the St. Lawrence Estuary is the result of the mixing between cold and oxygen-rich water from the Labrador Current and warm and oxygen-poor water from the Gulf Stream. This water dives at the bottom of the Laurentian Channel and starts a 3 to 7 years journey toward the end of the channel, completely isolated from the surface. During this journey, oxygen is consumed. And over the course of the last decade, oxygen concentration at the head of the Laurentian Channel decreased and is below the hypoxia level since the 80s. This is a consequence of various factors, but mainly of the changes in ocean circulation. In this presentation, we are interested in the consequences of bottom water deoxygenation of bioturbation activity and the consequences on sediment biogeochemistry. We hypothesize that water deoxygenation reduces the oxygen availability for macrobenthic communities, resulting in less active communities and larger accumulation of reduced solute in the sediment. To test the influence of deoxygenation on bioturbation activity, we sampled intact sediment cores at 5 locations along the oxygen concentration gradient. We assessed particle mixing rate and maximum penetration depths of organisms within the sediment using luminophores, which are fluorescent particle tracers. After an incubation time, the sediment cores are sliced at different depths. The slices are then freeze-dried and a subsample is photographed under UV light to automatically count the luminophores. Luminophores depth profiles are then used to compute a particle mixing coefficient as well as the maximum penetration depths of organisms. The assessment of bioirrigation is similar, but bromide is used as a solid tracer. And finally, oxygen distribution within the sediment was assessed using microsensors, and pore water samples were extracted for further nutrient analysis. Let's see the results. The relationship between bottom water oxygenation and bioturbation was analyzed using general additive models, which allow to account for eventual nonlinear relationships. First, the maximum penetration depth decreases linearly with oxygen concentration, suggesting that organisms go shallower into the sediment column as a response of low oxygen availability. Second, the result of our analysis showed that particle mixing and bioirrigation coefficients decrease with bottom water oxygenation as well. However, these decreases are nonlinear for both of these bioturbation processes. In fact, these bioturbation coefficients are fairly constant above the threshold value ranging between 84 and 54 micromolar of oxygen. Using the data from the work of Joanny Kuhl, this range could be narrowed between 63 and 54 micromolar of oxygen. Overall, this non-linear relationship suggests that bioturbation activity is maintained at a relatively constant level when oxygen concentration is above the threshold value, but drops below it. Now let's have a look to sediment biogeochemistry. The oxygen profiles show that oxygen penetration depth is about few millimeters and is shallower in hypoxic locations. Looking at ammonium profiles, we can see a greater accumulation of this reduced solute with depth in hypoxic location. The same pattern is observed for phosphate. It is worth noting that phosphate is usually trapped in the particulate phase in presence of iron oxide and is released in the dissolved phase during the reductive dissolution of iron oxide. Therefore, and although it is not a direct evidence, our results suggest a depletion of iron oxide with decreasing oxygen concentration. Interestingly, the depth at which phosphates start to be released in pore water is consistent with the maximum penetration depth of benthic organisms, suggesting here an influence of bioturbation and iron cycling, and more particularly the production of iron oxide, which could play a role of oxidative barrier in the sediment column. This barrier can buffer the production of reduced solutes and avoid their release into the water column. To conclude, in this study we have shown that bioturbation rates are relatively constant above an oxygen threshold concentration between 63 and 54 micromolar of oxygen. And below this threshold, bioturbation rates drop to near zero. Our results also suggest that bioturbation plays an important role in iron cycling through the enhancement of iron oxide production. Overall, this study highlights the importance of bioturbation in buffering the effects of hypoxia on sediment biogeochemistry. It also shows that the St. Lawrence estuary is at the dawn of profound changes and that we need to increase our knowledge on the effect of deoxygenation to better predict and manage the future of this ecosystem. And now, I just have to thank you for watching this presentation.